Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are on lecture 24 today and I am discussing about one of the most important aspects of this adhesion, that is JKR contact mechanics, and we have already gone through that how to derive the work of adhesion from contact mechanics and from the interfacial energy and work of adhesion and concepts, and we have derived in the last lecture this particular equation. Now, JKR contact mechanics, you have seen in the last lecture that it is quite rich, okay, in terms of the theory, but it is also very important, okay, in terms of the experiments, and that is what I will like to discuss this today, and you will see that it is a very useful experiment and the analysis also very interesting. So, now here we have this JKR equation like that, and so experiments that we do is I will come into a little later the detail, but in essence what we have is we apply different amount of P0 load and we measure A1. Okay. So, that is what we do in the experiments, and so this equation can be written a little bit differently, therefore, in order to help us in analyzing the data, and that is what we are going to do today. So, let us say that I write it something like this: 6 WA K pi, this is square root A1 to the power 3 by 2. So, this will be equal to K A1 cube by R minus P0. So, I can divide it further. So, I can write it as, I can divide it by A to the power 3 by 2, both the left hand side and the right hand side. So, then I will have 6 WA K pi to the power square root, that will be equal to, this will be K by R A1 to the power 3 by 2 minus P0 by A1 to the power 3 by 2, like that. And then what I can do is this, I will have write it little bit differently. Here let us say I will write it as, so let us say I write it as A1 to the power 3 by 2 by R, so P0 into the other side. So, yeah, so like that is equal to 1 by K here, and this is P0 by A1 to the power 3 by 2, right, and plus, so K I have taken the other side, so it will be K 6 WA pi by K to the power half, like this. So, here I will have taken it this term in the left hand side and divided the everything by capital K here, and so I have now this one as 1 by K into P0 by A1 to the power 3 by 2, and this K has been divided, I have divided K all the left hand side, both right hand side. So, I have finally here this equation which is actually here. So, in essence what I have is that if I replace capital K, okay, by 4 star by 3, and let us say I consider an incompressible material. For an incompressible material, this nu is equal to, this is 0 sigma is equal to 0.5 here. So, E by 1 minus sigma square. So, this is half, this is 4 by 3, this is 3 by 4, so it is 4 by 3, and K is equal to 4 star by 3. So, 4 by 3 into 4 by 3 16 E by 9. So, from there this expression I have this equation. Now, this is very useful. Here the experiment is done something like this. So, in a sense what we have is a, let us say, deformable sphere of the material which is attached to a motorized stage. This is a motorized stage, actually linear stage. This is a linear stage in which is displaced at a very small displacements are given. This is optical microscope, this is an weighing balance, and let us say that this sphere, deformable sphere, is brought in contact with this particular solid surface. Let us say this is a glass plate or a silicon wafer, okay, like that. And then this particular soft lens is can be a soft rubber lens, or like for example some silicone lens or like that. We say we are lighting lens because this is a this is in the form of a hemisphere basically, or a part of a sphere, okay, spherical basically. And now you using a motorized stage, you put it up and down, and let us say you increase the load continuously, you bring it down, so the contact area increases. Using the optical microscope you can measure the contact area, okay. And so here it is something like this. So let me play this movie here. So initially there is actually no contact, okay. So here already some contact has been made, so it is not exactly 0 load, but a little higher than that. And now the contact is being increased, and as you see that the contact is increased, the contact area increases, and that is captured by using the optical microscope. And then it is called the loading stage. And now once the final contact area, I mean let us say the load has been quite increased quite a bit, okay, in the range it has reached quite a bit, and the contact area is also quite high. Quite high means it is high with respect to large, with respect to the radius of that particular glass the hemisphere. And now you bring it in upward, means unload it. So when unload it, this contact radius, okay, again decreases. So the loading will be when it increases, and the unloading will be when you are decreasing it, and the contact radius this decreases. In both the time you measure the load by using this weighing balance. Now why weighing balance? You can use a load cell also, but weighing balance because many situations the load will be actually very small, okay, and weighing balance connected to a computer, okay, will be a good idea to have. So you attach a weighing balance by RS-232 or by some other means to an interface with a computer, and you have a motorized stage by which you to carry out these experiments, and you will get the data in this, as I said earlier, that P0 as a A1 as a function of P0. So you apply, so this is a kind of displacement control load control experiments. So you apply the different amount of load and you measure what will be the contact radius, that is A1, and then all the data can be written in this particular form, A1 to the power 3 by 2 by R, because you know that what is the radius of this particular hemisphere. Now remember that here, okay, that is what he was showing here, okay. Remember that this R, okay, here we have taken one solid surface, so where there are radius is actually solid surface is 0, right, radius is not 0, there is infinity because solid flat surface, okay, curvature is 0 here. Now radius is infinity there, and then you have got a hemisphere here, okay, which has got a finite radius. So basically the effective radius, let us say radius, relative radius of curvature, that will be 1 by r plus 1 by infinity. So therefore this this r, that is effective or the relative radius of curvature, that we using, that value r that we are using here is actually the radius of curvature of this particular lens itself, okay. Now instead of having this flat surface, if you had another lens, so for example let us say you have got another lens over here, then you can calculate, replace this capital R, okay, by calculating this 1 by R1 plus 1 by R2. Now we have gone through these things like that, okay. So correspondingly over here, if this particular plate is a glass plate or rigid substrate, okay, then the elastic modulus there is infinity, let us say, and so therefore when we calculate E star 1 by E star, right, then you calculate 1 minus sigma 1 square by E1 plus 1 minus sigma 2 square by E2. Now since E2 is much larger than E1, so do not worry about it, you have only this part, right. So that is the way it is. It is from that concept only we write here, okay, that E star is equal to 1 by 4 E by 3. So that is Poisson ratio is let us say 0.5 or something like that. Now it may happen that in a different experiment, as I have shown here, you have a soft adhesive layer, adhesive block, let us say, okay. I will not say block, a layer, because we have to have an elastic half space. So the dimension has to be large, we cannot have a very thin film. If it is a thin film, instead of an adhesive block, then this JKR mechanics will not work, okay, the theory will not work. But so therefore let us say you have got a quite a thick adhesive block, okay, the thickness of this is much larger than this contact radius. So that means H is much larger than A, let us say, and you have this glass hemisphere. Now, let us say that instead of having a soft lens, you have a rigid glass. So, both the ways it will work. Okay? The theory and the analysis works in either way, right. So, here like that. Now, here again you, by using a camera and all that, you are applying, you are measuring this, you are capturing the contact radius, contact area, which is circle because it is a sphere, and then you obtain the like that. So, you obtain loading and unloading, okay, different contact radius, contact area, and then you have the data like this, as I was telling you that the data with respect to, let us say this is P0 here, with respect to P0, and this is the contact radius. So, the contact radius, it first increases up to this point, let us say, okay, this is loading stage, and then this is unloading, okay, that is what it is there. And so, if you plot this data of versus A as a function of P, right, this is a load control experiment. So, P is the x axis and A is the measured value parameter, okay. So, you will get the data like that. Now, you see that this is the loading data, that is the open circle, and the unloading data filled circle, and they are both the data, they fall on each other very nicely, right. And so, what we can do is we can scale this P by A data with respect to this kind of result, okay, this kind of law. I mean, like, so you write, you obtain A1 to the power 3 by 2 and divided by R 5 millimeter here, and P0 like that. So, here the result, the load is given in terms of Newton because we are following MKS unit, and then this is in meter. So, you can see here that the contact radius that we obtained is actually very small. I mean, like, it is maybe about 0.2 millimeter here, 0.7 millimeter here. So, it is much smaller than the 5 millimeter the radius. So, that is the way it is. So, let us say now you have the data here like that, and so you obtain A to the power, A basically A1, P0 and A1 I should say, to the power 3 by 2, and then you divide it by R, and so basically you have this P to the power P0 by A1 to the power 3 by 2 here, A1 to the power 3 by 2 by R here, and you can obtain it in an Excel sheet, okay, or you use some other software, MATLAB and all that, you can do that, and you see that this data for this particular case falls so nicely on a straight line. And as I said, the open symbol is the loading and the filled symbol is unloading, and both the data nicely superimpose on each other, and you get a constant slope for both the cases. So, remember this equation that we try to fit to this data here, something like this, something like this. So, here this particular equation, the slope, okay, of this plot A1 to the power 3 by 2 by R as a function of P0 by A1 to the power 3 by 2, okay, the slope of this equation has the information of the elastic modulus, and then there is an intercept there which has the information about the work of adhesion. So, that is the beauty of this particular contact mechanics, that here you see by one measurement P0 as a function of A1 or A1 as a function of P0, you get two kinds of information. One is about the Young's modulus or elastic modulus of this material, and the second one is about the work of adhesion. That means what is the interface about, okay, what is the interfacial state about, that is about you get. So, you get both the things, both that but you see in addition you get something else also, and that I will come in a minute, come to the point in it. So, you see that here, okay, from the slope you can obtain the elastic modulus here, and this is the intercept over here. From this intercept you will get the work of adhesion. So, what it means, intercept means that at the 0 contact load, at 0 load, when P0 is equal to 0, then also you have some amount of finite, okay, contact radius. So, that contact radius, whatever it is, that gives rise the idea about the work of adhesion. And if you extend this line to the back over here up to this point, you see you will get this value at which the P becomes equal to, becomes negative, okay, P becomes negative, and this A1 tends to become actually 0, okay. So, the 0 contact load, okay, 0 contact area you get at this kind of pool of load, that is all it gives. So, you get lots of information, okay, from this JKR analysis. So, you get the elastic modulus from the slope data, from this intercept data you get the work of adhesion. So, for example, here the slope comes out to be 2 into 10 to the minus 7 in the appropriate units, and the intercept comes out to be like this. So, you can actually obtain the slope from the slope data, the elastic modulus. So, elastic modulus, the slope is 9 by 16 E, that is equal to this. So, therefore, E comes out to be close to about 3 megapascal, and the intercept is something like this. So, from there work of adhesion comes out to be 53.5 millijoule per meter square. So, this is a typical silicon, okay, with a glass surface, somewhat modified glass surface you will get, where hydrogen bonding and other interactions are not there. Okay, dispersive interaction you will get very similar to it, maybe little smaller, like that. Now, what is interesting here, that this loads in the loading state, the force versus this the y versus x data in the loading cycle and the unloading cycle, they superimpose. Okay. So, what it means is that there is no hysteresis in this case. Okay. So, during the whatever work of adhesion during the loading stage and the unloading stage, okay, that remains equal. So, what it means is that here this when it in this particular case, let us say that when you increase the load, okay, the interfacial properties that does not change, okay, that remains unchanged, and when you decrease the load, okay, so therefore, the loading and unloading during the both the times at the similar load, the contact radius actually remains same. Okay. So, that is an interesting aspect about it, because that is not going to happen always. So, that is why when it does not happen, then it is the hysteresis, and so that also we can get. So, now here for example, here is another set of data from some literature and paper, in which we have plotted, the authors have plotted like that, and you see here that there are several sets of data, and in each case it defines one particular kind of material. So, what it means is that this slope defines 9 by 16 E here. So, what it means that as the Young's modulus increases, the slope decreases, or Young's modulus decreases, the slope increases. So, here in this direction the Young's modulus actually decrease, and then the slope therefore actually decreases, and so what it means is that you can also compare between materials, okay, by this load versus displacement experiments, and where you can, by analyzing the data, you can also get actual exact value of the Young's modulus or the modulus of the material as well. Okay. So, those are the various advantages of this, or various aspects of this JKR contact mechanics, but there is something more, and I will come to that in a minute. So, let us first discuss a small problem, and we will then we will discuss about what is known as the hysteresis. I will touch upon that point little in a small way today. So, let us say that an experiment is conducted to measure the adhesion force between a BSA functionalized bovine serum albumin. So, that is a protein molecule. So, BSA functionalized AFM tip and a hydrophobic substrate in water. So, people are interested in measuring the hydrophobic interaction of protein with a hydrophobic surface in presence of water and blah blah. So, various kinds of interest are there, and so what is the how a protein molecule will interact with a hydrophobic surface, and that to that is the question. And so, here that is being done by using this AFM, and the AFM tip, as you know, it has got, it looks something like this if you magnify it, and it has, this particular tip has got a diameter. So, this diameter is 2.5 micron. So, radius is 1.25 micron, right. And so, this particular surface that we have, that hydrophobic surface is being said. So, the water will form a contact angle of 103 degrees, right, it is like this. So, let us say it is water, and this angle will be 103.7 degree according to this problem. And then diiodomethane, so diiodomethane is a, so water is a polar molecule, diiodomethane is a non-polar molecule. So, non-polar interactions, this is a surface that we have is hydrophobic glass or hydrophobic silicon, hydrophobic. So, hydrophobic once again is non-polar. So, non-polar interaction will be better. Okay. So, therefore, this diiodomethane, which has a lower surface energy. Okay. So, water is here and diiodomethane is here. So, diiodomethane, okay, it will it has got actually higher dispersive interaction. So, that spreads on this particular surface. I am not sure if I wrote correctly over here, I have to see in the next slide what value I took. So, anyway I will see. What the problem says is that calculate the theoretical work of adhesion between the tip and the substrate. So, that is all you need to do. So, remember that we need to find out the interaction, the adhesion between the theoretical adhesion force between the substrate and the tip. So, the tip is functionalized BSA functionalized AFM tip, that is the thing. So, what exactly you have to do? So, what you have to do is that we know from the surface energy is already given. So, let us say what is the surface energy of this surface, that is not given, this hydrophobic surface, this surface energy is not given, and this, although on this surface water from this contact angle that is given, and the surface energy of the tip that is also not given. However, the contact angle that water will make and the diadomethane will make on this surface that is also given. Okay. So, basically contact angle data for water and diadomethane on this surface and the tip surface, okay, both are given. So, both these things are given, and not only the surface tension of water, but the dispersive polar component and dispersive polar component are also given. Okay. So, here please note that this should be actually 0. Okay. So, from this data we first need to find out what is the surface tension or surface energy, okay, of this hydrophobic surface and of this tip surface, that we need to find out. Okay. So, if we find out that gamma tip and then gamma surface here, let us say, then we can use this Young-Duff equation or the Good-Girifalco equation to obtain the interfacial energy of this tip and the surface, hydrophobic surface. So, we need to get the interfacial energy between tip and the hydrophobic surface, and that from there we will be able to get the work of adhesion. That is all you need to do. So, it is not much, but little bit. So, let us see. So, for example, over here for this case, now gamma LL is 72.8, that is the water, let us say, into 1 plus cos theta, 1 plus cos theta. So, theta is 103.7 is equal to 2 into, okay, here gamma SP not known. So, gamma SP we need to find out, gamma L is we know 21 point P. So, 51, P is 51, that is for water. Right, and then 2 here square root, and this is gamma S, this is D here, and this is 21.8, 21.8 here, like that, right. So, you have, this is one equation, and the second equation will be with respect to diadomethane, and the diadomethane the total, this is 0 here. So, this is 50.8. So, this is 50.8 into 1 plus cos, the angle here is 63.7, 63.7. So, 63.7 is on the surface of this hydrophobic surface, that is the contact angle of diadomethane. So, this is equal to 2 into, okay, this is gamma S P, and this is the 0 here, because this should be equal to 0, because diadomethane has 0 here actually, and polar component surface energy, and gamma S D here, gamma S D is D, and then it has the 50.8 is the dispersive component, 50.8, that is quite a lot, okay, like this. So, now we need to solve these two equations, what I have solved of course, and we have obtained like this. After solving this, gamma S, okay, comes out to be 26.4, this comes out to be 0.3 millinewton per meter, and this is 26.7 millimeter per meter. Remember that this is a hydrophobic surface, okay, I had described in a previous lecture. For hydrophobic surface, okay, there are molecules, non-polar molecules attached to the glass surface or silicon wafer. So, therefore, it should have very low polar component of the surface energy, and that is what we get here. Now, for the tip also we need to do the same thing. For water on the BSA functionalized tip, this is 72.8 into 1 plus cos of. So, what is the contact angle of water? 61.3. So, this is 61.3 here is equal to 2 into, this is gamma SP. So, this is 51 into gamma SP, no, gamma SP only I want to find out. So, gamma SP is basically gamma tip here. So, let me write down its T in terms of T here, okay, and this is P, and gamma L will be 51 and plus this is 2 square root and this is 21.8. So, before that I will write gamma T D here into 21.8. Okay. So, similarly I have to write for 51 I guess, yeah 50.8, this is 50.8 for diadomethane, this is 50.8, 50.8 into 1 plus cos of, this is 61.3, 27.1. So, 27.1 degree is equal to 2 into, this is gamma T into P into 0 here plus 2 into 50.8 into gamma T into D here, like this. So, here again you solve this two equations and you get the surface energy of the tip surface, which is functionalized by this by BSA. So, you get like that. So, you have now the values of the surface energies. So, what you need to do is to calculate this work of adhesion, because if you know the work of adhesion, then only you can apply, you can calculate the pull off load. So, that is what we will do here. So, let us say that this gamma SW I write it like that, gamma TW I can write it like this, gamma ST I can like that, I had done something like that in the previously. And so, here remember that this SW that gets cancelled, because if S and W gets cancelled over here. So, you are left with this 2 T. So, this gamma T here, you get 2 T here and minus this quantity, this should be 2 T here, 2 gamma T here and like this. So, now you substitute all the values that you have estimated. So, finally, gamma W 2 gamma W, yeah, water. So, finally, you get here and then you substitute these values and of these numbers and you will get an expression their value for the work of adhesion. This comes out to be 54.76 millijoule per meter square. So, which is actually millinewton per meter, same thing. So, from the JKR theory, the pull off load I have calculated earlier to be 3 by 2 pi r W. So, this is the pull off load that we have shown earlier. So, you use this value over here. So, it will be 1.5 into P into 1.25 into micron. So, 10 to the power minus 6 here into this is 54.76 into 10 to the power minus 3. Okay. This many millijoule per meter square, millinewton per meter. So, if you do all that, we get in terms of Newton, you get in terms of Newton over here, and this value comes out to be 322.6 nanonewton. So, that is the amount of force that will be applied, okay, and required to be applied to separate this BSA functionalized tip, okay, from this hydrophobic surface. So, I will stop here today and I will talk about this hysteresis in my next lecture. Thank you for your kind attention.